Hello and welcome back to Machine Learning. I'm Javita Christie, and in this video, we are going to talk about feature engineering, and we will continue with feature transformation. In the previous two videos, we talked about feature construction. Now we're going to talk about feature extraction, which is another method of feature transformation. So let's begin. In feature extraction, new features are created from a combination of original features. So this would particularly help you if you wanted to reduce the number of dimensions in your dataset. And some of the commonly used operators for combining the original features include if you have Boolean features, which means features that have only two values like yes and no, you could use conjunctions, disjunctions, negation, etc. to combine those features. If you had nominal features are categorical variables that do not have any significance in terms of hierarchy, like class A, class B, or hair color, eye color, stuff like that. So then you could use Cartesian product, or you could use M of n, which means out of n features, you could select some of those. The third one, if you have numerical features, numbers, continuous features, then you could use minimum, maximum, addition, subtraction, multiplication, division, average, equivalence, inequality, and more such things to perform feature extraction. Here is an example of a very simple feature extraction where there are four features A, B, C, and D. We have converted those into two features by using these formulas. Feature 1 is equal to, you have 0.3 into feature A plus 0.9 into feature A. Actually, it's probably B or something over here. And feature 2 is feature A plus 0.5 into feature B and plus 0.6 into feature C. So we're just using those features to convert into these two features. So you could apply any kind of formula and reduce the number of features. Now there are several techniques to do this, feature extraction. The first one of those techniques is known as the principal component analysis, which is also known as PCA. So let's take a look at that. In PCA, a new set of features are extracted from the original features, which are quite dissimilar in nature. Okay, so the original features that are quite dissimilar in nature, those kinds of features are extracted. So if you have an n-dimensional feature space, it could get transformed into an m-dimensional feature space where the dimensions are orthogonal to each other, that is completely independent of each other. Okay, so that means if you have a couple of features that are associated with each other, then you could just combine them and create one feature. So in the end, what happens is you end up having features that are not related with each other at all. And this kind of a technique would also help you if you were doing, say, regression analysis, and you found that some of your predictor variables or X variables are related to each other, are having some linear relationship, which is also known as multicollinearity, which, if you remember, is a problem in regression. So to solve that problem, you could use PCA, because what it does is it finds out features which are closely associated with each other, and it would convert those features, it would combine them and convert them into new features. And so whatever new set of features you get will be orthogonal. Orthogonal means they are not at all related to each other. And the objective of PCA is to make the transformation in such a way that the new features which are created are distinct. Okay, so there is the covariance between them is 0. And the principal components are nothing but the new features that you have created. So they are generated in order of the variability in the data that it captures. Okay, and so the first principal component should be capturing the maximum variability. and the second one should be capturing the next highest variability, etc. Okay, so it is about how varied your data is and how much of that variability is captured by your feature. And the feature with the highest variability will be the first principal component. The sum of variance of the new features of the principal components should always be equal to the sum of variance of the original features. Okay, so just because you reduced the number of features, the total variability of your data set should not be reduced, because data set is still variable, is still having its own variance, and because you reduced the features, you should not have less variance. The variance should remain same. And PCA works on the basis of a process which is known as the eigenvalue decomposition of a covariance matrix of a data set. Okay, so now these are very mathematical terms, and hopefully if you have taken any calculus classes and you remember some of it, you would know what an eigenvalue decomposition is. I'm not going to get into the details of that here. So there is eigenvalue decomposition of a covariance matrix. We know what covariance is because we have studied that in the videos on probability and statistics. Okay, so what are the steps for PCA? First, you will calculate the covariance matrix of your data set. Then you will calculate the eigenvalues of the covariance matrix. And then the eigenvector that has the highest eigenvalue represents the direction in which there is highest variance. And so this will help you in identifying the first principal component. So that's how you begin with PCA. You create a covariance matrix, calculate eigenvalues, and then see which eigenvector has the highest eigenvalue. That would be your first principal component. And the fourth step is that the eigenvector having the next highest eigenvalue would be representing the direction in which data has the highest remaining variance and is also orthogonal to the first direction. So this would help you to identify the second principal component. So notice that it says that the second, the eigenvector which has the second highest value will lead you to the next principal component, which will be completely orthogonal to the first one, which means it will have no similarity with the first principal component. So like this, you have to keep on identifying the top k eigenvectors having top k eigenvalues if you want k principal components. So you can decide how many principal components you want, and based on that, you can select that many eigenvectors, top eigenvectors. The next method that you can use to perform feature extraction is the singular value decomposition. This is also known as SVD. So this is a matrix factorization technique which is commonly used in linear algebra. And what happens here, you take SVD of a matrix A which has m cross n dimensions, is a factorization of this form. So this is the matrix A, which is equal to U and sigma V. What are U and V? So U and V are both orthonormal matrices, and here U is going to be an m cross m unitary matrix, which means it consists of ones and zeros, and V is going to be an n cross n unitary matrix, and sigma is an m cross n rectangular diagonal matrix. So I'm sure you know all these terms because you've studied matrices. Okay, and what are the diagonal entries? So diagonal matrix would have values only in the diagonal. And so what will be there in the diagonal? The entries which are there, they are known as the singular values of matrix A. And the columns which are present in U and V are known as the left singular value. So columns in U are left singular values, and left singular vectors, and columns in V are right singular vectors of matrix A respectively. So that is how you can do singular value decomposition using that formula. So SVD is generally used in PCA once the mean of each variable has been removed. Okay, since you could use SVD along with PCA to perform feature extraction. And it's not always advisable to remove the mean of a data attribute, especially when the data set is sparse, right? So if your data set is not very big, it's not advisable that you remove the mean of the attribute. So SVD is a good choice for dimensionality reduction in such situations where you have less number of columns in your data set. SVD of a data matrix is expected to have the following properties. What are those properties? Number one, patterns in the attributes are all captured by the right singular vectors, which means all the columns of V. Patterns among the instances are captured by left singular, which is the columns of U. Instances are nothing but rows. And larger a singular value, larger is the part of the matrix A that accounts for and its associated vectors. And the final point is new data matrix with K attributes is obtained using the following equation. D dash equal to D into V1, V2, and so on up to Vk. So these are all the vectors that we calculated. And this is how you can get a new data matrix with K attributes using this equation. Let's take a look at the third kind of method, which is linear discriminant analysis. Another commonly used feature extraction technique, just like PCA or SVD. And the objective of this particular technique is similar to this, to the sense that it intends to transform a data set into a lower dimensional feature space. So the idea is the same, that you want your data set to have less number of dimensions than what it had previously. But unlike PCA, the focus of LDA is not to capture the data set variability. So in PCA, if you remember, we were talking about which feature captures the maximum variability of the data set. That feature would be the first principal component, and then the second principal component would be capturing the variability, but it would have the second highest variability. So that's how PCA works. But in LDA, we are not talking about data set variability. Instead, LDA focuses on class separability. That is, separating the features based on class separability so as to avoid overfitting of the machine learning model. And we have seen what overfitting is in our previous videos, where the model works so well with the data set with which you have trained it that it stops working well with data that is new, data that it hasn't seen before. So that is known as overfitting, when it fits so perfectly to the training data that it no longer is able to classify new data that's coming in, which it has not seen before. Okay. And unlike PCA, that calculates the eigenvalues of the covariance matrix of the data set, LDA calculates eigenvalues and eigenvectors within a class and interclass scatter matrices. Okay, so what happens in LDA? It calculates the eigenvalues and the eigenvectors, but only within a class and interclass scatter matrices. And what are the different steps? So first step is you will calculate the mean vectors for the individual classes. Okay, calculating the mean vectors for the individual classes. The second step is to calculate intra-class and interclass scatter matrices. In the third step, you will calculate the eigenvectors and eigenvalues and eigenvectors for SW1 and SP. What are those? SW is the intraclass scatter matrix, and SP is the interclass scatter matrix that you calculated in step 2. And so here you can see the formula given. SW is sigma I equal to C. C is number of classes. And this is your matrix. What is SI? SI is equal to this. X belongs to DI. DI are all the dimensions from I to N. Simply do X minus MI into X minus MI raised to T. Here MI is the mean vector of the I's class. And what is SB? SB is this. Sigma I equal to 1 to C. Ni into Mi minus M into Mi minus M raised to T. So once again, Mi is the sample mean for each class. M is the overall mean of the data set. Ni is the sample size of each class. And after doing this, you will identify the top k eigenvectors having the top k eigenvalues. So that is how you can find out the features that are going to be important, extract the features that are going to be important for your machine learning model and can improve the performance of your machine learning. And so once again, there are three techniques: principal component analysis, SVD, singular value decomposition, and LDA, which is linear discriminant analysis. All three of them are feature extraction techniques. And I know they are very mathematical, and maybe you need to have a lot of mathematical background to understand all of these. So we are going to be leaving this feature extraction topic right here. I hope you understood everything that was explained in this video, and I'll be back with the next one. Thank you for watching.